So today we're going to be working on numbers on the complex plane. And so what the complex plane is it involves an area called lateral numbers. What we are used to up until this point is numbers that either go in one direction or in the other. We have what we call the positive and the negative axis. You either have more of something or less of something. What we're introducing when we say the complex plane, we're now saying, hey, we can have something else. And what this means is that, let's say you have 2 apples, and I have 2 oranges. If I have 2 and you have 2, we both have 2, but you don't have more fruit than me. You have a different type of something. I can take your apples away, but that doesn't necessarily add to my value. We're looking at, and that may not be the best analogy, but the idea is we're comparing something new, something that's still 2 units away. You're still 2 units away from being hungry, but we're not in the same direction. You have an apple, I have an orange. So we're introducing a second dimension to the number line. And this is what we call lateral numbers. Now, the fun part is a lot of students ask, well, why does I represent a lateral number? Why wouldn't L represent a lateral number? They almost look the same. Why use an I? Well, that comes from way back when mathematicians called René Descartes, when they were first looking for what is the square root of a negative number. They were looking at quadratics and how they work out, and he said, hey, these things are impossible. You might as well call them imaginary. Along several other things, and several other mathematicians said, I cannot find a use for this thing. Why don't we just say this is stupid? It's imaginary. It's impossible. You can do this math, but it doesn't mean anything in the real world. So they started denotating it as I for those impossible imaginary numbers. A couple centuries later, we come around, we find that in fact these lateral numbers have many different uses, especially when we go down to quantum mechanics in the quantum realm. A lot of different forces use things that represent lateral numbers. A lot of computer programming use them as well. So albeit in his time, René Descartes said these are impossible, I will never find a use for them. We have in fact found that this is a highly useful skill, especially as computer software is developing. So it's worth figuring out how do numbers work in the lateral plane. So let's take a look. Whole idea is I is the square root of -1. So if I have I squared, I will get -1. That's the idea. So whenever we break down any sort of square root, typically we would break it down into 2 different square roots. I'd say, okay, a -49, I'm going to break this down into the square root of -1 and the square root of 49, both of which I can find values for. The square root of -1 is going to give me I, because what number times itself gives me -1? I. When I say what number times itself gives me 49, I get 7. So my final answer is 7I. Boom. Likewise, if we don't want to break it down into just 2, let's say 98. 98 isn't a perfect square, so we're going to have something left over. So first off, let's break down 98 into the square root of -1 and the square root of 98. Now 98 I can divide by 2, so I'm looking at the square root of 2 and the square root of 49, of which I know the square root of -1 is I know the square root of 49 is 7, but unfortunately I can't reduce down my square root of 2. So in this case I have a 7 and an I with a leftover square root of 2. Now, the same thing works for these numbers as do variables. If I have variables in here, most of the way that we're going to break these down is by factor trees. Now, I'm not going to write out the square root each time. Typically, the way that we write these out is we would write them out as a -1, a 16, and then the older fashion for these variables is I would write out an x and an x. What I would do right here is I would say 4 and 4. and I would circle pairs of numbers. Okay, the square root of 16 is 4 by 4. I have a pair of 4s, which means a 4 can be rooted out. I have a pair of x's, which means an x can be rooted out. Likewise, I know that -1 can be broken down into I and I, which means additionally an I can be rooted out. So I have an I, a 4, and an x. These being accepted constants, I'm going to say 4i followed by my variable. Perfect. That's an alternative way to write it. This is to utilize the root symbol each time. This is to go for bases and say, I'm not caring what the square root of 49 is. I want to find bases. And this will help you if perchance you don't spot the roots immediately. So let's say with this one, I don't spot the roots immediately. I say I have a -1 and a 300. I say I have a 3 and a 100. I don't recognize that this is a perfect square. Let's say I continue to break it down into a 2 and a 50, a 2 and a 25, and I say, hey, I recognize that the 25 is a 5 and a 5. Well, what I can do is I can say, hey, I'm going to pull out a 2 and pull out a 5. Likewise, my I and my I, I'm going to pull out an I as well. And with my W's, 1, 2, 3, I'm going to pull out 2 W's. Now, unfortunately, I didn't pull everything out. I still have this 3 left behind, and I have this other W left behind. And what this means is that my 2, my 5, my I, and my W all come out. My 3 and my W get left behind. Then I simplify what I can. 10iw square root 3w. This is what we call the split factors. Boop, boop. 2 and 2, because they're at 2 different spots on the tree, they'll root together to make a square root of 2. I could have alternatively done this question. Let's say I take the square root of -300, w cubed, and I do it like we did in number 3. And I say, okay, that's the square root of -1 times the square root of 300. That's the square root of 3 times the square root of 100. This is going to be the square root of w squared and the square root of w. I know that I can break down 3 of these roots. That's going to give me an I, that's going to give me a 10, that's going to give me a w. I have to leave behind the 3 and the w. In this case, I have a 10iw square root 3w. Either way that you do this, with the split factors, where you circle pairs of numbers, or if you just recognize where your perfect squares are, you can do either way. So what I want you to do is I want you to try out number 9 and number 11. I want you to pause the video, give them a shot, resume it when you're done, and see how you did. Okay, let's see how we did. So the first way I'm going to show using the traditional method. I'm going to say right here I have the square root of -1 and the square root of 25. Right here I have the square root of x squared because squared and squared will make x to the 4th, and the square root of y squared. All of which, 1, 2, 3, 4, and 5, I can root. Square root of -1 is I. Square root of 25 is 5. Square root of x squared is x, x, and y. If I reorganize that, I have a 5ix squared y. Perfect. The second one, because I don't know the square root of 160, I'm going to break this down according to the split factor tree. I get a -1 and a 160. I get a 2 and an 80. I get a 2 and a 40, 2 and a 20, 2 and a 10, 2 and a 5. I have 1, 2, 3, 4, 5, 1. Okay? So I have 1, 2. It's going to come out. 1, 2 that's going to come out. Oh, and I know right here, I know an I is going to come out. I left behind a 2, a 5, an N, and a Z. So if I rewrite that, I have I times 2 times 2 times N. Left in the square root, I have 2 times 5 times N times Z, which is going to simplify to 4IN squared, square root of 10NZ. And there we go. So today what we're going to be looking at is numbers in the complex plane, mainly what we call our I tables. Now our I tables, what we've got here is I've got I up to the 20th power. We're going to know something very special about that. Remember, if we know that I is equivalent to the square root of -1, what we know is that when I multiply I times I, I'm going to get the square root of -1 times the square root of -1. Or when I put those two together, that is the square root of -1 times -1, which is the square root of -1 squared, or -1. So I'm going to get a -1 value in there. I itself is just going to be I. So I have -1, and if I multiply that times another I, I'm just going to get a negative I. And I to the 4th is I squared squared, so what is -1 times -1? I'm going to get a +1. So far, so good? Well, if I keep adding the square root of -1, multiplied times itself again and again, here I have I to the 5th. Well, I know I to the 4th is 1. I know I to the 1st is I, so 1 times I is I. I to the 6th can be broken down into I to the 4th, which is 1, and I squared, which is -1. So in essence, I have 1 times -1, which is -1. I to the 7th, again, it's just I to the 4th, which is 1, times I to the 3rd, which is -I. So 1 times -I is going to be -I. And I to the 8th is just I to the 4th times I to the 4th, which is 1 times 1, which is 1. And then at this point, we should notice that there's a pattern going on here. Our I tables repeat. I have I, -1, -I, +1. I, -1, -I, +1. Or if you want to look at it as every other, have I, -I, I. Or I could say -1, +1, -1, +1. Boom. We've got a pattern here. Every 4th I value creates a pattern. So I know the number that comes after +1 is I again. Then I know it's going to be a -1. Then I know it's going to be a -I. Then I know it's going to be a +1. In which case I repeat the pattern. I, -1, -I, +1. I, -1, -I, +1. Boom. And so our I tables are going to really help in understanding what happens when we start multiplying by numbers. So down here, basically all we have is we have no more than, I think, I to the squared. But let's go ahead and take a deeper look. So when I distribute an I amongst anything, I'm going to distribute it just like I would a normal number. I would say I times 5 is going to be 5I. The big thing that happens here is when I multiply it, I'm going to get plus 4I squared. And as we've just discussed, what is I squared? -1. So it's actually 5i plus 4 times negative 1. So 5i minus 4. And then the last thing that we need to pay attention to is lateral numbers or complex numbers are always listed in what we call A plus BI format. We always list the real part first and then the lateral. So I'm going to say, okay, my real one is negative 4. My lateral one is 5. So I'm going to say negative 4 plus 5i. There we go. So for number 3, I'm going to do the exact same process. I'm going to distribute my 5i to both these terms. And I'm going to get a 50i minus 60i squared. I know I squared is negative 1. So I'm going to get 50i minus 60 times negative 1, which is just 50i plus 60. And then I'm going to write it in the A plus BI format, which means I'm going to list this number first, 60, and my 50i second. And that's it. That's really all that's involved with multiplying i's, even if it's as complex as binomials. If I have this, I'm just going to distribute each term. 2 times 3 is going to give me a 6. 2 times I is going to give me a 2i. I times 3 is going to give me a 3i. I times I is going to give me an I squared. Now the cool part is when I multiply two complex numbers together, because this is really one complex number, I'm going to end up with one complex number. My i's combine, I get 5i. This is going to turn into a negative 1. So I'm going to end up with a 6 plus a negative 1, which is just going to be a 5. So I have a 5 plus 5i as my answer. Awesome. And so what I want you to try and do is I want you to try number 7 on your own. Pause the video, knock out number 7, resume it when you're done, and see how you did. Okay, so what you might have noticed is that number 7 is a little different. Same process, but something cool happens. I multiply this positive number times this positive number, or this complex number times this complex number, and I get a 100 minus 10i. And then when I multiply this, I get a plus 10i minus I squared. I notice my two complex numbers cancel out. My two lateral aspects go away. And what I'm left with is I know that this I squared, that's 100 minus negative 1. That actually turns into 100 plus 1, which is 101. And there's a cool mechanic behind that, and it has to do with how we actually multiply number lines and the visual mechanic of what's going on. What we have right here is that if I were to, let's say, multiply a number like 2 times 3, they're both in a singular direction on the number line, with 0 being over there. I would say, okay, I'm going to go 2 groups of 3. So 3, 3, and I'd end up at 6, because they're both heading in the same direction. Now, with my complex numbers, basically what we're doing is we're going off the number line. If I have my real axis and I have my lateral axis, I know if I go 10 plus I, there's my first number, 10 minus I, there's my second number, I'm going to end up multiplying my two real aspects, 10 times 10, I'm going to get 100, and my two basically lateral aspects are going to cancel each other out. Part of it's going up, part of it's going down. They're going to completely do away with each other. And I'm going to end up back on the real axis. So we'll get more to that in a future lesson, but just to show you that when we multiply complex numbers, we're really dealing with more of a vector system. But let's move forward. Let's try this one again. For this one, when I distribute, I get a 12 minus 6i. When I distribute my lateral aspect, I get a 24i minus 12i squared. And now two things happen. I combine my lateral aspects and I get plus 18i. And for these, I'm going to get 12. That's 12 times negative 1. That's going to be a plus 12, which is going to be a 24. My 18i is just going to hang out, not causing any sort of a ruckus right there. And so over here, we notice it's the same pattern. I have a 2 plus some complex aspect, 2 minus some complex aspect. So I bet you I'm going to end up back on the real axis. I get 4 minus 10i plus 10i minus 25i squared. My complex numbers cancel out. My I squared changes that. So that turns into minus 25 times negative 1. So that is just 4 plus 25, which gives me a 29. And so again, kind of what we're seeing here is we're seeing another aspect of what's going on. My 2 plus 5i in this case is 2, 1, 2, and then I go up 1, 2, 3, 4, 5, and then I go 2, 1, 2, 3, 4, 5. I notice that the real number trajectory, 2 by 2, is going to give me a 4. And then I notice that the lateral trajectory, because they cancel each other out, rotates itself. And I get that result right here and I end up at 29. But again, we'll get more into these mechanics at a later date. But there we go. So today we're going to introduce the quadratic formula. Now, this is an incredibly important formula because it's going to break down a really big aspect of what we normally hand factor for, and it's going to allow us to find the roots of any quadratic, regardless of whether or not it can be hand factored. And it's based off of the idea of something called the vertex and the discriminant. And now, without getting into too complex of an analysis, the idea behind any quadratic is if I have a quadratic and I have my, let's say, drawn like that on the axis, what I know is that from my vertex, we know that this thing is symmetrical on the left side versus the right side. So if I can find that central point on the x-axis, I know that the distance over here is the same as the distance over here. Now my drawing might not be exactly, but I know that this distance is the same thing as that distance. So if I find this point and I know this distance, I can add it and subtract it from my vertex and get root 1 and root 2. So without, like I said, getting into too much of a description, too much of a lesson of that distance on a quadratic is going to be what we call the discriminant. And we find that by using b squared minus 4ac. So the quadratic formula is built off of saying, okay, I'm going to take that vertex, negative b, or 2a, and I'm going to add and subtract, add the distance to root 1, subtract the distance to root 2, but I know it's going to be the same thing both times, and I'm going to use this, the discriminant, which is going to be b squared minus 4ac. And again, let's not get too caught up in how we created that, but the idea is that we find the vertex, add the distance, and take the distance back away. Boom, we'll have each root value. So today, all of our quadratics are going to hand factor. So you could actually hand factor each one of these, but we're not going to because I want a chance to practice this where it works out nice and neat. Not all the time will it work out nice and neat, but it's a good way to introduce this topic so you can check your work when you're done. So let's go ahead and use the formula. I'm going to take x equals negative b over 2a, and I'm going to both add and subtract the discriminant, so the b squared minus 4ac. All I need to know is my a, my b, and my c. So my a is my number out front, my b is the number in front of the single x, and my c is the number without an x. So let's go ahead and plug that into the formula and see how we do. Cool. So my a here is 1. So 4 times a over 2a. My b is 8, so negative 8, 8 squared. My c is 16. And so 98% of the quadratic formula is not necessarily understanding how to create this. It's an arithmetic process to simplify what you see right here. Nothing crazier. We've got our two roots. I'm going to start simplifying it. So that's a negative 8 plus and minus 8 squared is 64. 4 times 1 is 4. 4 times 16 is negative 64. All over 2. I know 64 minus 64 is going to be 0. Perfect. And so at this point, what we're going to do is I am going to split. I'm going to split it into an x equals a negative 8 plus 0 over 2, and x equals negative 8 minus 0 all over 2. And I'm going to solve each one of these. Negative 8 plus 0 is just negative 8 over 2, which is negative 4. Negative 8 minus 0 is negative 8 over 2, which is negative 4 again. Awesome. So we notice that the discriminant here is a 0, so that must mean that my vertex has no distance between the roots, and the only way that we would get that, let's just use this line for example. Let's say this is the line of the vertex. If my vertex was right here and it curved, I would have a positive discriminant. The only way I can get that gap to be so tight is if my two roots are on the vertex. So I'm going to see something that looks like that. Get rid of that right there. I'm going to see something that's so close that the two roots are on top of each other. And now again, you can't actually prove this by hand factoring. We're not going to worry too much about it. The idea is that, boom, we take the vertex and we add and subtract that distance, and we'll get the two roots. So what we've got right here, I need to find my a, which again is 1. I need to find my b, which here is 3, my c, which is negative 10. And I'm going to plug it into the formula of vertex plus or minus the discriminant. Okay. Let's plug in our values. Let's see, negative b, which is 3, b squared minus 4 times a times c, all over 2a. And so again, most of the quadratic formula is not some complex process, it's just simplifying what you've got right here. And so this is arithmetic, and we're really confident in our skills with arithmetic. So that's a negative 4 times 10 is a positive 40. Okay. So at this point, I have x equals negative 3 plus or minus the square root of 49 all over 2. And so I'm not quite at the point where I'm going to split yet because I haven't fully simplified my graph. I'm going to come over here and say, okay, x equals negative 3. I know the square root of 49 is 7. Now I'm going to split. So x equals negative 3 plus 7 all over 2. I'm getting that root. And I'm going to get x equals negative 3 minus 7 all over 2. So then I'm going to subtract the distance. So I'm going to add the distance and subtract the distance and get my 2 roots. That's 4 over 2. There's my first root. Over here I got negative 10 over 2, which is negative 5. Perfect. There we go. So knowing what we know, what we're going to do is I'm going to identify the A, the B, and the C. I'm going to give you the formula, and what I want you to do is I want you to give this a shot. Pause the video and resume it when you're done and see how well you did. There we go. So pause the video. There's the formula. There's your A, your B, and your C. Plug those in and see how well you do. Let's see how we did. So in this case, I have a negative 15. I have a negative 15 squared, negative 1, negative 50, negative 1. And so here's our first catch. What a lot of you probably did was you said, okay, if I need a negative b, my b's already negative, you probably just plugged in a negative 15. But be careful, because I want a negative whatever b is. So if b's negative, I want a negative, which makes that a positive. The second thing that you probably did, if you weren't paying attention, was negative 15 squared. What many of you probably did was you squared 15 and you said 225, and then you made it negative. Remember, most of the mistakes in quadratic formulas are not in the process, it's in simplifying what you've got. Negative 15 times negative 15 is positive 225. And lastly, again with negative signs, negative 4 times negative 1 is positive 4, times negative 50 is negative 200, all over negative 2. Cool. So then I'm going to take that, and I'm going to say, okay, x is 15 plus or minus the square root of 25. And that's going to give me 15 plus or minus 5 all over 2. And at this point, I'm going to go ahead and I'm going to split. I'm going to find the distance to the right by adding it. I'm going to find the distance to the left by subtracting it. There we go. So how'd you do? Let's try it a few more. Let's just give this a shot. These are both just further examples. Nothing crazy, just making sure our arithmetic is good. So let's go ahead and plug this in. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. In this case, my a is no longer just a 1 or a negative, it's actually a number in and of itself. Not that 1 wasn't a number in and of itself, it's just a bigger number. There we go. 13 is 4 times a and times c all over 2a. There we go. So I get negative 13 plus or minus 169. Let's see. That's going to give me, well, 2 times 15 is 30. 4 is 120. Cool. And so at this point, I'm going to split. So I get x equals negative 13 plus 7, so I can get that distance to the right. I get x equals negative 13 minus 7, so I can get that distance to the left. There we go. And so if you followed that same logic on number 9, let's go ahead and knock number 9 out real quick as well. Like I said, all we're doing right here is we're just practicing plugging in our values, practicing the arithmetic involved in reducing this. Again, I notice that I'm taking a negative of a negative, which is going to end up making that a positive. So I get a positive 16 plus or minus, let's see that, I think that's 256. Okay, so 3 times 21 is 63. That's a positive 63. 4 times 60 is 240. 4 times 3 is 12. 240 and 12 make 252. Okay, I keep going. And I can actually reduce this. That's going to give me an x equals 8 plus or minus 1, negative 3. And in this case, now that I've fully reduced everything I can, now I'm going to split. So x equals 8 plus 1 over negative 3. And x equals 8 minus 1. It's the distance to the right and the distance to the left. There we go. Compare that to see how you did. And that's it. Okay, so today we're going to be doing the quadratic formula again, but this time the discriminant is not going to be a perfect square. I'm going to get irrational roots. And remember, if we get irrational roots, like let's say the square root of 20, we're going to break that down into whatever roots we can. So if I get, let's say 4 and 5, I can take the square root of 4, which is 2. I cannot take the square root of 5, and I'm going to leave that behind. And we're going to get some aspect that looks like this. And the cool part about irrational roots is that if one's irrational, so is the other. Because remember, we're looking for the distance. So if I know the distance over here is some sort of square root, I know the distance on the flip side is also going to be a square root. One irrational root comes with a pair with another irrational root. That is a general rule that will be applied. So each one of these is going to have 2 irrational roots. So let's go ahead and get started. The same process applies today as yesterday. We're going to take the quadratic formula, which is negative b over 2a, and we're going to add and subtract the discriminant, which is b squared minus 4ac. I'm going to take the square root of that. All we need is I need to know my a, my b, and my c. A is the number in front of x squared, b is the number in front of x, and c is the number with no x. So let's go ahead and plug that in and see how we do. So negative plus or minus 4ac over 2 times a. So that's a negative b plus b squared minus 4 times a times c all over 2a. So it's negative 8 plus or minus, let's see, that's a 64 minus 44 over 2. Oh, lo and behold, our first example is going to be the same thing as up here. So x equals negative 8 plus or minus the square root of 20 all over 2. And so what we're going to do is we're going to take a quick pause and take the square root of 20 and see if we can't reduce that. We already know that 20 breaks down into 4 and 5. I can take the square root of 4, which is 2. I cannot take the square root of 5, so I'm going to leave that. So I'm going to rewrite this as x equals negative 8 plus or minus 2 square root of 5 all over 2. And then the last thing that we're going to do is we're going to check out, hey, can I, I'm going to use blue for this, can I reduce this fraction? And the answer is yes. Both 8 and 2 both divide by 2. So negative 4 plus or minus 1 square root of 5. Now, with this, typically speaking, this is going to be where we stop. You could split it, but remember, this doesn't reduce any further. So if you split it, you're just going to be writing out. Let's split this. So that would be x equals negative 4 plus the square root of 5, which gives me that right root, and x equals negative 4 minus the square root of 5, which is going to give me the left root, which is no different than what we were showing right there. So let's do one more of those. So what we need is I need to know my a, my b, my c. A is the number in front of x squared, b is the number in front of x, and c is the number with no x. I'm going to plug it into the formula, which involves taking the vertex and then adding and subtracting the discriminant. There we go. Let's plug in our values. Negative 8, 8 squared, negative 1, 15, negative 1. And if we start simplifying this, it's going to be a positive 4 times 15 is going to be a positive 60. Okay. X equals negative 8 plus or minus the square root of 124 all over negative 2. And again, we're going to take a quick pause. Square root of 124. We're going to break it down. So I noticed in this case, 4 goes into 12 and 4, which is going to be 31. I can take the square root of 4, which is 2. I cannot take the square root of 31, which means that that can be broken down into x equals negative 8 plus or minus 2 square root of 31 all over negative 2. We're going to ask ourselves if I can reduce both the tops, and yes we can. X equals negative 8 divided by negative 2 is going to be a positive 4. 2 divided by negative 2 is going to change the sign. So you can either leave it as plus minus because I'll still have a plus minus, or if you want to be super fancy, you could say minus plus. Really, there's no difference between minus plus and plus minus. You have one of each. If you wanted to split it, basically what would end up happening was you would have an x equals 4 minus the square root of 2 times 31. Oh, hold on. 2 doesn't exist because 2 divided by 2 is 1, which means that this doesn't exist. It's just 4 minus the square root of 31. And my other one would be x equals 4 plus the square root of 31. You have your two answers. There we go. So I want you to take that as an example. I want you to pause the video, try out number 5, resume it when you're done, and see how you did. Okay, so let's get down our A, our B, and our C. We're going to plug that into our quadratic formula. Okay. My B is negative 9, my A is negative 1, and my C is negative 17. Perfect. My negative 9 is going to be at positive 9. See, that's 81. Negative 4 times negative 1 is positive 4 times negative 17 is going to be negative. See, 2 times 17 is going to be 34. It's going to be 68. Perfect. X equals 9 plus or minus square root of 13 all over negative 2, which in this case, I can't reduce 13 like we did before, so it's just going to stay that. Awesome. So let's get just a few more. Let's do 2 more of those, make sure we got the process down. So again, the big thing that you're going to be doing is you're just going to be finding your A, your B, and your C. A is in front of the x squared, B is in front of the x, and C is the number without x. And you're going to plug it into your formula, which is your vertex, negative b over 2a, and you add and subtract the discriminant, which is b squared minus 4ac. So in this case, I get negative 16, plus or minus 256, minus 4 times 3 is negative 12, times 12 is negative 144, which in this case is, let's see, that's 1, 1, 2. Okay, so we're going to take a pause and find the square root of 112. Let's see, I know it's even, so I'm going to divide it in half, which is 56, 7 and 8. This looks like a split table, so it's 2 and 4, so I'm just going to go ahead and split it all the way down and circle my pairs instead. Cross out a pair, cross out another pair, which means 2, 2, and the 7 stays behind, which is 4 square root of 7. So the 7 stayed behind, my 2's canceled out, and my other 2's canceled out. So I have x equals negative 6 plus or minus 4 square root of 7 all over 6. I notice that I have some reduction that can go on. X equals negative 3 plus or minus 2 all over 2. There we go. So for the last one, go ahead, pause the video, give it a shot, resume it when you're done, see how you did. Let's see, A, B, C. Plug it into your formula. And simplify. Don't forget a negative b is a negative negative. It's positive 12 times negative 12 is negative 144 over negative 6. Go. In this case, I can actually split. I guess we had a real one slip in there. So I have an x equals 13 plus 5 over negative 6. X equals 13 minus 5 all over negative 6, which gives me 18, which is negative 3. And negative 4/3. And There we go. So today what we're going to be going over is the third part of the quadratic formula. And now all of these are all going to have lateral roots. What that means is the fact that when we have our quadratic graphed, we're going to be graphing a quadratic that doesn't actually touch the axis. And we notice that what happens is the fact that we know that these actually don't touch the x-axis somewhere we can see. The problem is that we know the fact that with the math, we're going to get two roots. That's going to be the square root of some negative number, which means I'm going to have two answers that pop up somewhere. And what we notice is the fact that these two answers are going to be behind or in front of the x-axis. They're going to be on the lateral axis. So if we take our graph and we rotate it, and I rotate our previous graph right here, but in this case I give it a front and a back. So instead of having an x, y, I have my x and my y, and I've rotated the graph out. What we know is that this graph is going to have two roots in the x-axis way back here, which in essence means that this is going to be more like a tunnel or a slide. So let's go ahead and see the true shape of a quadratic by looking at some of these lateral roots. Okay. So first off, we know that with any quadratic, using the quadratic formula, I'm going to identify my a, my b, and my c. And I'm going to take it and plug it into the quadratic equation. Negative b over 2a, which is my vertex. And I'm going to add the distance to one root, which is the square root of b squared minus 4ac. We also call that discriminant. So that's going to give me my root on the right. And then I'm going to also take it away, which is going to be my root on my left. And so let's go ahead and plug this in and see what exactly happens. Oop, tried to fill in an a there. Awesome. So here I know my b is 2. My a is 1. Oop, that's a 1. My b is 2 and 2. My a is 1 and 1. My c is 5. And let's start working this out. So I have a negative 2 plus or minus, well, that's a 4. Negative 4 times 1 is negative 4 times 5 is negative 20. 2 times 1 is 2. And so you already see a problem of brewing right here. X equals negative 2 plus or minus the square root of negative 16 all over 2. And the problem that we run into right here is if the square root of negative 16, if that were only a negative 1 and a 16, we'd be able to do it. So the square root of negative 1 is I. The square root of 16 is 4, which means this is actually 4I. So we're going to rewrite this as x equals negative 2 plus or minus our 4I all divided by 2. I know I can divide both of those by 2. It's negative 1 plus or minus 2I. There we go. We know the fact that it's going to cross the lateral axis, 1 at 2I and 1 at negative 2I. Perfect. So let's go ahead and take a look at the next one. Remember, the first thing we're always going to do is identify our A, our B, and our C. And we're going to plug it into the quadratic formula, which consists of the vertex, which is negative b over 2a. And for 1, I'm going to find the distance to the left root, which means I'm going to subtract the discriminant, which is b squared minus 4ac. And then I'm going to find the distance to the right root, which means I'm going to add that. So I get my two roots by adding and subtracting the distance to the root from the vertex. Here we go. And so all we're going to do is we're going to plug in my b, which is 2, my a, which is 1, and my c, which is 17. Let's see how this works. We have 2 plus or minus, that's a 4. 4 times negative, or negative 4 times 1 is negative 4 times 17. Let's see, 17 times 2 is 34. It's going to be a minus 68. So again, your first clue that this is going to be lateral is you see that this is about to be a negative number, which you know means it won't actually hit the graph on the real axis. And so now we notice that in the negative 64, if I could only break that down into a negative 1 and a 64, I could root both of these. I know that this is an I, and I know this is an 8. So I could use 8i. So let's rewrite this instead of square root of negative 64 as an 8i. There we go. And again, we can reduce this by saying both of these divide by 2. Perfect. There we go. And so now, what I want you to try and do is I want you to try number 5, pause the video, resume it when you're done, and see how you did. Okay, so let's take a look. I have my A, my B, and my C. Plug it into my formula. My B is 2, my A is 2, and my C is 5. As I work this out, negative 2 plus or minus 4. Let's see, that's 8 times 5 is minus 40. Again, we notice that this is going to end up being negative, so I know it's going to hit laterally. Square root of negative 36. I know that negative 36, if I break that down into a negative 1 and a 36, I can square root both of those perfectly. I and 6, or just 6i. So we get x equals negative 2 plus or minus 6i all over 4. Now this I can't fully reduce, but I can divide all three numbers by 2, which says x equals negative 1 plus or minus 3i all over 2, which if this was a radical, we'd just be done. But again, when we have lateral numbers, we want to split it into the real and the lateral aspects. So I'm just going to break these both down into negative 1/2 plus 3/2 I. So that way I know I go half a unit to the left on the axis, and I go forward 3/2 on the lateral axis. And that gives me what we call, I believe, rectangular form given complex numbers. Perfect. So how are we doing? Looks like we're doing pretty good. So let's give another shot at one of those. Now that you're a little familiar with how we break it down, see if you can't break this one down a little faster. I'm going to go ahead and pop the work on here, and let's see how you did. Now, one of the things you'll notice that I do is that often I go ahead and I write out the quadratic formula, even though many of us just go ahead and say, hey, I know what my A, my B, and my C is. They just plug it in. What you'll end up doing is by writing this out, A, you commit this to memory. B, one of the big mistakes is that you saw me do it, where you'll put the wrong letter in the wrong spot. This is a very easy formula where a lot of people make very simple mistakes. So I always recommend writing it out. And the good thing about that is that when you write it out, you'll catch little things like this. Where here my B is a negative 4. And by writing it out, boom, boom, I see that I have a double negative, which is going to turn that positive. One of the big common mistakes we talked about previously is that that negative 4 somehow keeps a negative because students see negative B Well, my b is negative, so therefore that becomes negative 4. And that's an incorrect assumption that by writing the full thing out, you avoid it. A is 4, MIC is 5. So I'm just a big proponent of writing it out. So 4 plus or minus 16. Let's see, 4 times 5 is 20. Negative 4 times 20 is negative 80, which again, we notice that it's going to hit laterally right here. Negative 64. And so I think we're comfortable enough to notice that if I have a negative 64, I know that's going to give me an x equals 4 plus or minus. The real square root of 64 is 8. And because it's a negative, it's going to be 8i. So we're going to skip that middle step. If you don't feel comfortable skipping the middle step, don't worry about it. Include that. You can always write out negative 64, negative 1, 64, and then square root both of them. Get your I8, which is 8i. You're always welcome to do this. Nothing against that. I can divide 4a and 8 by 4, which gives me 1 plus or minus 2i all over 2. I know I want to split this into the real and the lateral aspect, which brings me to x equals 1/2 plus or minus 2 halves I, which is really just saying x equals 1/2 plus or minus I. So now this one hits 1 on the right and then 1 forward on the lateral axis. And I guess the other one would be 1/2 and 1 backward on the lateral axis. Perfect. So let's take a look at this one. Last one. Pause the video, try this last one, resume it when you're done, and we'll see how you did. Okay, let's take a look. Okay, plug it into our formula. My B is 2. My A is 5. My C is 10. See, 4 times 5 is 20, times 10 is 200. I know that is negative 196. Now the square root of 196 is 14, which means that is negative 2 plus or minus. In this case, square root of 196 is 14 because it's negative. It's going to be 14i. I can divide the 3 of these by 2. And then I'm going to split it into a real, 1/5, and a lateral, which is 7/5 I. So I now go left on the x-axis by 1/5, and I go forward on the lateral axis by 7/5, and I go back on the lateral axis by 7/5, and I have my 2 roots. And there we go.